you have seen sunsets like this? Your screen, your room, your surrounding, your whole reality is nothing but light entering into your eye. In everything you do in your life, in your day-to-day life, you are already using the concepts of light. What is light exactly made of? Said that light is a particle. Others said light is a wave. In my prism, when the light enters and it disperses into 7 colors. How many of you have seen sunsets like this? Almost everyone. Orange, calming, almost magical. Or how many of you have fairy lights in your room to give your room a cozy feeling? Or if not in person, how many of you have seen northern lights dancing in the sky in one video or the other? Now, all these three are very different phenomena. But what is the one thing that was common in all these phenomena? And write down today's topic, my friend. That is your chapter, light. Your screen, your room, your surrounding, your whole reality is nothing but light entering into your eye. But here is where things get interesting. It's not as simple as it looks. Light bends, it reflects, it splits into colors, and we are going to decode that exactly today. How the color of the sky gets orange at sunrise or sunset, how the fairy lights become so warm and cozy, and how northern lights play these amazing games in our sky. All these links back us to the chapter light. Now, we know that light is everywhere. But why should I study this? You know, in our class, there was one kid that always said, "Ma'am, why should I study this chapter?" Well, I was that in my class. And my teacher told this very amazing thing that still is in my heart right now. She said, "Aditi, you know, you use your specs every day." I said, "Yes." When you wake up in the morning, you go and you get ready in front of the mirror. I said, "Yes, of course, everyone does that." Or you go out and after that rain, you see that beautiful rainbow. I said, "I love that." She said, in everything you do in your life, in your day-to-day life, you are already using the concepts of light. And those are exactly what we are going to study in this chapter today. But this is not just a chapter. Here is where things get interesting. It also links to some of the most powerful career paths out there. How? If you want to be a doctor, you have to have knowledge about the magnifying glasses, about the microscopes. If someone came and want to have a LASIK surgery, you should know what the eye lens, how my eye lens works. Right? How it resonates with the light that is entering into the eye. Or if you want to become an engineer, you build a face recognition structure, or you build a self-driving cars. All those machines are based on one single thing, that is how those machines understand light. If you want to go into photography or filmmaking, you have to know how your camera reacts to the light. Right? And that is exactly we are going to study today. So the outline for this chapter will be very basic. We'll start what is light, then move to reflection, refraction, and power of a lens. So now first, what the first thing comes into your mind, ma'am, what is light? Right? What is light? So light is a form of energy. What? Light is a form of energy that enables us to see this pretty world around us. That is light. Right? It's a form of energy that enables us to see the world around us. But what everything is made of something. I am made of atoms, molecules. You are made of atoms, molecules. What is light exactly made of? What is light exactly made of? So in here, we got two very brave scientists. They came forward and they said, one said that light is a particle. Others said light is a wave. And we got confused. What are you trying to say? Is it a particle or a wave? Be very clear. So then we got to know, we got two scientists. First one was our very own Isaac Newton sir. Isaac sir came and they said, see, look, light is actually a particle. He called it as corpusculus. Now we call them as photons. You must have heard. Photons. And he said that they are having a speed of 3 × 10⁸. 3 into 10 raised to power 8 meter per second. But after some time in 1600s, again Christian Huygens G came. Christian Huygens said that no Newton, wait, this light is not actually a particle, it is a wave. And he said that light consists of electromagnetic waves. That means it has an electric component and a magnetic component. You will study that later, don't worry. It's an electromagnetic wave which do not need any material medium to travel. And we said that that is right. We know in space we have vacuum, but light comes from sun to earth. That means it is traveling in vacuum. It does not need any material medium to travel, right? Like my sound needs air. It cannot travel in vacuum. If you go into the space and you call out, Aditi ma'am, you'll feel like, I won't be able to hear your sound. But with light, that's not the case because I'm still able to see you in the vacuum, right? So two approaches were there. Either light is particle or light is wave. So we were like, what is the conclusion? What is the conclusion? What exactly is light? So we came up that light is actually having dual nature. That means according to its need, it acts as a particle sometime, or it acts like a wave sometime. So if light acts both as wave as well as particle, and it changes its behavior according to what is in front of it, right? We also act according to a situation presented to us, right? So light also does that. How it does that? See, you have seen solar panels, right? So in solar panels, when light comes and it hits that solar panel, it reflects back, right? But in that case, it acts like a particle. But you have seen prism as well, maybe in your labs. So in my prism, when the light enters and it disperses into 7 colors. We will study that, don't worry. Right now, just remember it disperses into 7 colors, and that in this case, it acts like a wave. So we got two situations where light is acting like a particle, and in other situation, light is acting like a wave. Right? Now, okay, light has dual nature, but okay, in this chapter, we are going to study light. But how do we see objects with light? I know that light is this light is energy, but we should be able to see that ray of light, right? Not the object. The object is not the source of light. So this is where the question comes. How do we see objects? Why do we see objects? And that is, my friend, a very interesting topic, reflection of light. So what happens is, there is a light here. Okay, there is a light source here. This light hits me, right? It hits me and it reflects back. It reflects back. It bounces back off me. This light came, let's say this hand is my light. It came, it bounced from me and went into your eyes, right? So it came, it bounces back and entering into your eyes, and thus that object which it bounced from gets visible, right? So it is the bouncing back of light when it strikes a surface without getting absorbed. If the light gets absorbed, it won't bounce back and enter into my eyes. Pretty simple, right? So you have a torch. When you click that on button, when you on the torch, it reflects, it throws some light, and it made the object visible right in front of you that you want to see, right? So it bounced back from that object, the light went, bounced back from that object, came back and hit me in my eyes, and that is how I was able to see that object. Correct? Then now let's dive a bit into physics of it. Now we study reflection, but there are some laws of reflection. You also have some boundaries in your home, right? That you can go out till 8 p.m. You can go out till 7 p.m. After that, you have to come home. Similarly, reflection, light also has to go through some laws. It also has some laws that how it should go and how it should come back. Not when, but how. Okay, so the very first law is, there are 3 things. Understand it very simply. There are 3 things. The one, I had that flashlight, right? I had that flashlight. So it is going. The one ray, it is going. This ray, it's going. Correct? And then it is one ray, it reflects here and then it goes back. Correct? So these are the 2 rays. So the first ray that comes without bouncing, before bouncing, the ray that is coming, this is called my incident ray. And the one that bounces back after the bouncing back, this one is called reflected ray. So we have incident ray that is coming, incident ray, it reflects from the mirror and it goes back. That is called reflected ray. Understood? Now, there is one very important topic, that is normal. Now, let's say, this is my mirror, okay? This ray came, and this ray went back. So, this is incident ray, that is reflected ray. But one very important thing is, if you take one more line and place it perpendicular to this surface, right? Perpendicular to this surface, that, my friend, is your normal. So, a plane, a line, it is kind of imaginary, but a line that is perpendicular to your mirror, it is perpendicular to your mirror, that is your normal. And why this is important? Because all the measurements we take is according to the normal. Let's understand. This incident ray is coming. Now we have a thing called incident angle. What is that incident angle? So the angle this incident ray is making, this angle with the normal, this incident ray is making an angle with the normal, and that angle is called angle of incidence, at which angle my ray hits that mirror with respect to normal, is called your, so this is your normal, this is your incident ray. Then similarly we have reflected ray. So what the reflected ray makes with the normal, that angle is called angle of reflection. Understood? These basic normal terms are clear. Now let's move on to the laws of reflection. Now laws of reflection first said that we studied about angle of incidence and angle of reflection. So the first law says that always pretty skies, if the sky turned green one day, angle of incidence will be always equal to the angle of reflection. That means if this angle was 30 degrees, then in any circumstance, this reflected angle will also be 30 degrees. If it is 40 degrees, it will be 40 degrees, 50 degrees, 50 degrees, 60 degrees, 60 degrees. Doesn't matter. Angle of incidence will always be equal to your angle of reflection. Done? Now this is done. Now second law is a bit tricky. So listen carefully. Okay, but it's very interesting. Now let's say I hit a ball on the wall and it comes back. But there is one thing that ball does. It hits and it can technically go into any direction. Right? But there is one thing different in case of light. If light is coming like this, so if light is coming like this, it will hit the mirror. Let's say my hand is the mirror and this is a plane. Just plane, imagine a plane. So this comes right here, the light goes, this is the incident ray, it will reflect back and go like this. It won't do this, and it went like this. That's not possible. If it comes in a plane, it will go back in the same plane. So they are saying that incident ray and my reflected ray and the normal. So normal, you will make the normal like this. This is your incident ray, reflected ray and normal. Everything will lie in the same plane. Let's study. The incident ray, the normal to the mirror at the point of incidence. So where the incident ray is incidenting, this point, where the ray is actually hitting, that point, on that point if you make the normal and then the reflected ray, all three of them will lie in the same plane. Understood? All of them will lie in the same plane. We have a ghost for you here. Done. So these two are the laws of reflection. Those are very, very, very important. They can directly ask you in the exam. These laws are very important. They'll directly ask you to write the two laws of reflection. Done. Understood? Now, next thing is very, very, very tricky or important, let's say. Right? So, next is image formation by plane mirror. Ma'am, why is this tricky? This is very easy. But this is easy. If you look at it, it's easy. I told you. But actually, light is not that easy. Right? So, we are going to study the basic of how image is being formed using the plane mirror. Now, see beta, in this chapter, we are going to study some optical instruments. What? Optical instruments. That means plane mirror, lenses, spherical mirrors. So, all these kind of things you will understand after you study the basics. And that is your plane mirror. Okay, so we'll study the image formation by plane mirror. So every day you wake up, you stand in front of the mirror and you do your makeup. That is your plane mirror. Why? There are some of the technicalities there, let's say, that makes it a plane mirror. First of all, the size of the image is equal to the size of the object. So when, let's call this Rohan. So when Rohan is standing in front of the mirror, he won't see a big head and a small stomach and big legs. He will see him as the same size that he is, that his body is. Right? So that means the size of his body, the size of the object never changes. It is equal to the size of image is always equal to the size of object. That is one thing. Second is image is formed as far behind the mirror as the object in front of it. So let's say this is again my mirror. So if in front of the mirror I am 2 meters away, let's study it from here. Let's say Rohan, what do we call that? Rohan is 10 meters from the mirror, is standing 10 meters from the mirror. Now, this image, his image will also be 10 meters from the mirror as well. He is standing on the right hand side of the mirror. His image will be on the left hand side of the mirror, but both will be at equal distances. Right? Both will be at equal distances. The image is laterally inverted. A very heavy word. Ma'am, what is laterally inverted? Laterally inverted is nothing but lateral inversion. That it horizontally switches. Like this is my hand. In the mirror, it will look like this. Right? It will look like this. That means the left side of my hand will look like it is my right hand. And the right hand will look like it is my left hand. That is it. That is it. Basic. Okay. Thus, image formed by a plane mirror is always virtual and direct. Let's study this virtual and direct a bit later. Okay. We'll study this virtual and direct a bit later. Now, what do we say? We are moving to spherical mirrors. So, the mirrors that are not plane mirrors, first of all, that means the size will not be same, the distance will not be same, it won't probably be laterally inverted. It might be laterally inverted. So what are spherical mirrors? The reflecting surface of spherical mirror may be curved inwards or outwards. That means it actually looks just like you. Like you are standing right now. You are sitting right now like this, watching your screen. No? Straight back. Come on. Okay. Now, there are two kinds of spherical mirrors. Let's just see. First is your concave mirror. Second is your convex mirror. Now, how do we study this and what are exactly this? Let's say you have a sphere. Let me find something that is round. Okay, no. Let's say you have a sphere, you have a ball and you cut that ball in half, right? So, that ball will look something like this now. That ball will look something like this now. Right? So, if you hold that ball, this is your ball, and if you send a light ray in the inside part of the ball, and that reflects back. That means the inside part is reflecting, the inward part of the ball is reflecting, right? So that part, if the inward parts, let's see, a spherical mirror whose reflecting surface is curved inwards, the inwards part of the surface of the mirror, if that is reflecting, then that's, and it faces towards the center. So if I complete the ball, this is like this. So this is the center of the ball. So if the reflecting surface faces the center of the mirror, then it is called concave mirror. One more very important thing, how to remember this is, it looks like a cave, right? So that is concave. Ma'am, this also looks like a concave. Cave, right? But it is the opposite cave. You have to go inside the cave. If you go inside the cave, then that mirror is called your concave mirror. And if this part, the outside part, from here the light is coming, if from the opposite part the light is coming, then that is called your convex mirror. Just like this, the light is hitting the outside part. Now the inside part is not reflecting. You didn't break the ball. You took a ball and you sent some lights on it, right? So that is the outside part of the ball, right? So if light reflects it, if light hits the outside part of the ball, or let's say outside part of the mirror, then that is called convex mirror. A spherical mirror whose reflecting surface is curved outwards, whose reflecting surface is curved outwards, whose reflecting surface is curved inwards. So concave, curved outwards is convex. Done? So we are done with convex and concave mirrors. Not done, we just started it, but we understood the basics. These are two kinds of spherical mirrors, concave mirror and convex mirror. Now let us understand the terminology. Let me just switch my screens and let's go to this. Now, terminology for spherical mirrors. This is very, very important. We know two kinds of mirrors are there. That is your concave mirror and your convex mirror. You did study, right? Now, if the mirror is curved inwards, if your mirror is curved inwards and the outside part is non-reflecting and the inward part, that means this part is reflecting, this is, my friend, your concave mirror, right? It's going inside the cave. If the outside part of the mirror is reflecting and the inside part is shaded, it's closed, and this part is reflecting, light is coming, going like this, right? So this is convex mirror. This is your convex mirror, where the reflecting part is outwards. The outward surface is your reflecting. Right? Now we need some things to understand the basic. Now see, what our goal is here to study the image formation, right? For that we need some very basic things to study, right? And for that we need to understand some very, very basic let's say points on the mirror. Let's say, now this is my convex mirror. Let's start with concave mirror. See, this is just the circle I completed. Now this is my concave mirror, right? This is my concave mirror. The outside part is shaded and the light is going in, right? So the light is going inside like this. Understood? Now these are few things you have to study. You took a mirror and from the center of this mirror, this is your mirror, let's say, and from the center of your mirror, you drew a line horizontally cutting that mirror. This is an imaginary line first of all, but this line, the point where it cuts the mirror, is called pole of the mirror. What is it called? Pole of the mirror. Now, if I complete this circle, extended this mirror and complete the circle or the sphere, we say it, then the center point of that circle, right? We know there is a center of the circle. So similarly, we have center of sphere. So that center is called center of curvature. center of curvature. Now ma'am, what is curvature? Curvature is simply how much your lens is bent. If this is if this is the mirror, then it has this curvature, but if this is the mirror, then it has more curvature, right? So the center of this mirror, this curvature, the center is called center of curvature. Done. Now we are done with pole, curvature. Now this length from center to the mirror, we normally call it radius. We have a circle and from center to the circle we call it a radius, right? In here it is also radius, but it is what? Here this R is radius. It is radius, but of what? Of curvature. Just like center of curvature, we have radius of curvature. Done? Then if you half that radius, listen to me carefully. This is the complete radius, right? If you further half it, the radius, this becomes the focal length. F becomes the focus. Let's say focus. That point becomes focus. Point F. That point becomes a focus, and that F, that length from the mirror to F, it becomes focal length. It becomes focal length. Understood? If anyone has any doubt, make sure you are commenting down and I'll get you through. Okay, don't worry, but listen to this carefully. There is a whole mirror. If you cut that through the line, this line is called principal axis. When you complete the circle, the center is called center of curvature. If you join the center of curvature to the mirror to the pole, that is your radius of curvature. If you half the radius of the curvature and this point comes, that point is your focus. And if you join the focus and pole of the mirror, that is your focal length. I know it can seem like a lot, but take it very easy, take it very lightly. Okay, tomorrow is not your exam. You're just studying, you practice it again tomorrow, you revise it again, and by the end it will be engraved in your brain. Trust me. Okay, now all this is done. And similarly, it is for convex mirror. This is your, so the whole length of the mirror, let's say the length of this curved mirror, it is called aperture. Similarly for convex mirror, this is center of curvature, radius of curvature, focus, focal length. Done? Very easy. Okay, now let's move to the rules of image formation by a first concave mirror. Since it's a concave, so that the cave, inside of the cave side is reflecting, right? Now again, we have some rules for image formation, just like you and I have rules, right? So the very first thing is, the object is, let's say at infinity, or let's say for now the object is anywhere. From that object, a light ray will come that will be parallel. Okay, so this is principal axis, right? So this light ray will be parallel to principal axis. This light ray will be parallel to principal axis, and after it hits the mirror, it will bounce back, it will reflect back. And remember, we studied one point, that was focus. It reflects back and goes into the focus. This is my focus. It reflects back, it goes into the focus. That means every time a ray will come parallel to principal axis, a ray will come parallel to principal axis, it will pass from the focus after a reflection. After reflection, it will pass from the focus. Always. That is the case for always. Anytime a ray comes parallel to principal axis, it will pass through the focus. Done? Next, we have, if a ray now comes from the focus, if a ray passes from the focus, it reflects back and goes parallel to principal axis. Okay, if the incident ray is passing from focus, then the reflected ray will be parallel to principal axis. And here, if the incident ray was parallel to principal axis, the reflected ray will pass from the focus. Done? Focus? Done. Okay. Then the third case we have, if we studied center of curvature, right? If a ray passes from center of curvature, very important point, it reflects back and passes again into from the center of curvature. It traces the same path. Incident ray passes from center of curvature. Reflected ray also passes from center of curvature. Then the fourth point, very easy. If it hits pole, we studied the pole. If incident ray hits the pole of the mirror, then the reflected ray will go at the same angle it came from. That is, this incident angle will be equal to the reflected angle. It will reflect back in such a way that the incident ray will be, incident angle will be equal to the reflecting angle. These are the 4 rules of image formation in concave mirror. First, incident ray parallel, it will reflect, passes from focus. Second, incident ray passes from focus, it reflects and goes parallel to principal axis. Okay. Third, it passes from center of curvature, goes back again from center of curvature. And fourth, if it hits the pole, the angle of incidence will be equal to the angle of reflection. Then, now let's move on to the actual ray diagrams. Yes, this ray diagram word is very scary. All of you must have heard that, dude, ray diagrams is crazy from your seniors, right? Ray diagrams are hard. Make sure you study ray diagrams. But let me tell you one thing. These are very, very, very easy. Like on another level easy. But only if you study now carefully. Right? If you practice again and again, this is very, very, very easy. Trust me. Okay, let's start, then you'll see. Let's see image formed by concave mirror. So the first case, when your object is at infinity, your object, this is your object. Your object is situated at infinity. That means I have a mirror here and the object is very, very, very far away. Let's say 10 kilometers away. So for this small mirror, 10 kilometers is like an infinity distance, right? So for a small mirror, 10 kilometers is an infinity distance. So how this mirror will make the image of that object that is standing 10 kilometers away? So for that, we assume that the object is at infinity. The object is at infinity, right? From there, we know that how rays will come. Now you studied that the first case, remember that whenever the rays come parallel, it will pass from focus. Now tell me, there is an object at 10 kilometer. Of course, all the rays will be coming parallel to the mirror, right? So very important point. When the object is at infinity, the incident rays will always be parallel to principal axis. Let me write it. The incident ray will always be parallel to principal axis. Done? This is my principal axis, right? Now let's make the diagram. See, a ray comes parallel to principal axis. Let's say another ray comes parallel to principal axis. Let's say one more ray comes parallel to principal axis. And one more ray comes parallel to principal axis. Now what will happen? Ma'am, we know whenever the ray comes parallel to principal axis, it always passes from focus, right? So let's make them pass from focus. This is my focus, right? This is your focus. Oops. This is your focus, right? So let's say this will reflect and it will go from the focus. Is it passing from focus? Okay, then this will also reflect. It will go back from the focus. Is it passing from focus? Yes. Then this ray also will reflect back, passes from focus. Done. Then third, it will go and passes from focus. Is it passing from focus? All the rays are passing from focus. Now that means wherever these rays are converging, let me tell you the meaning. Let's say all these rays are meeting at a point, okay? So these are meeting at focus. At one particular point, all these rays are meeting. Now this particular point is where your image will be formed. So your image, let me change the color. So your image will be at focus. Your image will be at focus. So what was the first case we studied? Ladies and gentlemen, the object is at infinity. Sorry. The object is at infinity, but the image is being formed at focus. How? If the object is at infinity, all the rays will come parallel to the principal axis. All the rays come parallel to principal axis. They reflect back, and we know the first rule that every ray that comes parallel to principal axis passes from the focus. It passes from the focus. Then, so image is being formed at focus, the object was at infinity. Now, there is one more thing that we need to study is we know position of image we studied. What is the nature of image? So, there are two things that we call as nature of image. Understand it very carefully. Now, look at this diagram we made here. Right? The rays are going and they are reflecting back, and the real rays are meeting. This ray went, this is the mirror, came back. So this ray, the original ray came back, right? That means the real ray came back. That means in this case, the image will be real. The image will be real, image will be formed. And with that, one more thing is there that we'll study in the next this case. Okay, let's study that. Okay. Now, let's say in the second case, first the object was at infinity. In the second case, we brought that object closer to the mirror. We brought that object closer to the mirror, right? So, let's say this is my center of curvature. This is my focus, right? And this is the pole. So, we brought the object very near to the mirror, but still very far away. Near, but still very far away. And this was beyond C. That is beyond the center of curvature. Done? Understood the position of object? So this is your object now. Where is your object? Beyond C. Beyond C. So sorry, my throat is a little bit itchy. Okay. Now, there are again 4 rules. How will you use those rules? First, very important point. Every time there is an object, one ray will be going parallel to the mirror. Obviously, some ray from this will go parallel to principal axis, right? So, this is my principal axis. One ray will go parallel to this principal axis, right? Correct? This ray goes parallel to principal axis, and ma'am, we know the ray that goes parallel to principal axis passes from the focus. So, it is passing from the focus. Done? It is passing from the focus. Now, remember, we studied one more rule. That was what? The second rule. If any ray passes from focus, then it will reflect back and come parallel to principal axis. It will reflect back and come parallel to principal axis, and the point where they meet, this is the point where they meet. This will be my image formation. Wait. This is the point where my image will be formed. Let me change the color of your image. This is the point where image will be formed. Understood? So, let's see once again. There was an object. A ray went parallel, passed from the focus. Another ray passed from the focus. Now, see. Of course, there are many rays that are going towards the mirror, but we want some rays that actually defines where the image will be formed. Okay, now there will also be one ray that is going from here and it's passing from here. So here, this point of the object is being made here, right? So that we don't need to study. We just need the lower point and the upper point. But lower point, ma'am, we don't see the lower point. Okay, now is where one very important comes. Listen very carefully. This is a bit scary. See, this is, let's say, the point A. This is the point B. From A, a ray went and it passed from the focus, and this is the point A, right? And let's say this is the point B. Now, again, one ray from point A went from the focus parallel to principal axis. Again, this becomes the point A. Till here, understood? Now, let's say from B, a ray came from the center of curvature. Now you remember the rule that when ray goes into the center of curvature, it reflects back, traces the same path. That means from B, the ray that came, it reflects back and went the same path. Went the same path back, right? So it again passes from center of curvature. That means now the B point will remain on the principal axis. This B was on the principal axis. This is my principal axis, right? So it was on principal axis. A ray came, went back to the same direction. So this B point remains on the principal axis, just its position shifts, right? That is why we say a word which is called inverted. Inverted. What does it mean? Here the object was standing tall. Here the object was correct. But when in the image it got inverted. First the object was like this. But from the image was like this. Done? Understood? First A was here, B was here. Now A is downside. It flipped, right? So A is down, B is above. This is called inversion or inverted. Correct? So here it is a point size image, but we'll come to the size once more again. But this is also the same. We can say that here it is inverted. So for all the cases of concave mirror, image will always be inverted. Image formed will always be inverted. Done. So here the image is formed where? First, image is formed between C and F. Image is formed between C and F. Right? So object is beyond C, but image is between C and F, my friend. Done? The object is beyond C. The image is between C and F. Done? Now here the nature is what? Again, real rays are meeting. So nature is real plus it is inverted as we clearly saw. So image is real and inverted. This is called nature of image. Right? So we have three things. We have position of image, we have nature of image, and one more thing, we have size of image. So we are done with position of image. Here the object is at infinity, position of image is at focus. Object beyond C, position of image is between C and F. In both the cases, the nature is real and inverted. Both cases, the nature is real and inverted. What is the size? Okay, so here we can clearly see it is point size. So the image is point sized. The image is point sized, right? In here, the image is not point sized. What? It is smaller than the object. It is smaller than the object. We can clearly see this was a bigger image. This was a bigger object. The image is a little bit smaller. So this is diminished. This is diminished image. That is called the size of image. The size of image is diminished. That means that image is smaller than the size of object. In plane mirror, we saw that size of image will equal to size of object, right? But see, in spherical mirror, the size of image is actually diminished. It is smaller than the size of object. Done? Let's move on to the next thing. Next case we have when we brought the object even more closer to the mirror. First, the object was at infinity. The object was at infinity. Then it was beyond C. Now we say that the object is at C. That means this is C, this is F. The object is not at infinity, not beyond C. It is at C. Done? The object is on the center of curvature. Now what will happen? Again, we'll take two rays. One ray that will go parallel to principal axis. It goes parallel to principal axis and then it passes from focus. It passes from focus. Done. Then another ray goes. It goes from the focus. It goes from the focus, comes back and meet at a point which is exactly below the center of curvature. Okay, this can be a little bit tricky to make, but in general, this point will be exactly below the center of curvature. Okay. So when you are making a ray diagram, make sure you are attempting it in such a way. Okay. So this is the ray, right? Make sure you are forming it in such a way that when these two rays meet, it meets exactly at a point below the center of curvature. Your end goal is at center of curvature. When the object is at center of curvature, the image will be again at center of curvature. The image will be, the object will be at center of curvature. The image is also at a point that is at center of curvature. Let me make this again. Yes. So the image will also be at center of curvature. Done? Understood? A ray came, a ray went, and it reflects back, passes from the focus. Another ray passes from the focus, went back parallel to principal axis. And the point where it meets, this is my image. So this was my object and this is my image. Done? So the position of object is at center of curvature. The position of image is also at center of curvature. Again, we know for concave mirror, every case, till I am telling you, every case is real and inverted. The nature of image is real and inverted. And one very important point in the case of at center of curvature, this is of same size. The image is of same size as of object. So if object is, let's say, 4 meters high, the image will also be 4 meters high. In this case, the image position will be equal to the object position, or image distance is equal to object distance, and the height or the size of image will be equal to the size of object. Done? And we know for concave mirror, it is always real and inverted. We can also see that real rays are meeting and the image is inverted. So it is real and inverted. Done? Let's move on to the next case. Okay. So the next case we have is between C and F. First it was infinity, then it was beyond C, then it was at C. Now it is between C and F. Let's say this is my object. Done. Again, one ray will go parallel. One ray will go parallel to principal axis and it will pass from focus. And it will pass from focus. Done. Another ray will go from the focus. It will go from the focus, right? And it will reflect back parallel to principal axis. And the point where they meet, will be your image. Now this will be your image. So this is your object and this is your image. Now one thing you can clearly see, the position of image. You have understood now? The object is between C and F. The object is between C and F. But the image is where? Now the image is beyond C. Clearly visible? Now the image is beyond C, but the object is between C and F. Done. And again, ma'am, this is real and inverted. This is real and inverted. Done. Now look at the size. Here the size of the object is very big, right? So we write it as a term enlarged, that the size of the image is enlarged. Size of the image is enlarged. Now it is not too big. Right? So if it is too big, we'll write extremely large, extremely enlarged. But here it is big, but not too big. So we'll write enlarged. Nature is real and inverted. Position is beyond C. Object position is between C and F. Understood? Easy. Now, do you think ray diagrams are hard? Just there are 6 cases, 8 cases. That's why you think it's too much. Don't. Just take it one step at a time. First thing, parallel. Passes from focus. Passes from focus, parallel. That's it. Till this time, 4 cases we have done. That is what we have done, right? Parallel, focus, focus, parallel. That's it. Done? Okay. Now, the 5th case. The 5th case, the image is now at focus. First, it was at infinity. It was at infinity. Then it was beyond C. Then it was at C. Then it was between C and F. Now it is at F. Right? So, let's understand now what will be the case if the image is at F. Sorry, the object is at F. Again, first thing is same. One ray will go parallel and it will pass from focus. Done. One ray will go parallel and it will pass from focus. Now second ray. Now here is a bit tricky part. 2 things you can do. We studied a case where the ray goes in center of curvature and passes again from center of curvature. So, it's a bit tricky, but let me show you. Let's say there is one ray that is going like this. Something like this. So it reflects and it goes back from the center of curvature. Then it goes like this, reflects, passes back from the center of curvature. So one thing you can do this, right? Another thing you can do, that one ray is hitting the pole, and then it is going back. It is going back at the same angle. That is angle of incidence and angle of reflection. Whatever these 2 suits you, the answer will be same. See, all these 3 rays are parallel. All these 3 rays are parallel. That means the image will be either. Okay, listen carefully. This is my object. Object is at F. So earlier, we used to say that image is formed at infinity. But according to the new NCERT, they have written that image is not formed. So you can write that image, of course, if the rays are not meeting, how will the image be formed? Right? So if the rays are not meeting, the image won't be able to form. So image is not formed. So understand carefully. If you keep any object, if there is object is in infinity, an image will be formed. Object is at C, beyond C, the image will be formed. But if this is my curvature, a mirror, and this is the focus, if I place my object here, the image won't be formed. How crazy is that? The image won't be formed, or you'll have to say image will be formed at infinity. That means this is my mirror, this is my object, and I have to place a screen at 10 kilometers away. That is crazy, right? So we say that image is formed either at infinity or not formed at all. Right? Very, very tricky case, very good case. Okay? But again, if you have to write, so nature will be again real and inverted. If it is forming at infinity, it will be real and inverted. Although they won't ask you this in the your exams, or earlier we used to write it extremely large, but now the image is not formed, so there is no size, no nature. So you can just skip it as well. Okay? Done. At focus. Now comes the 6th case. So every time you go talk to your senior and you ask them what are ray diagrams, they'll tell you 5 cases of concave mirror and 1 exceptional case of concave mirror, because this 6th case is again a bit tricky. Let's see why. We understand it. Okay, we'll not cram it. We'll understand why this case is tricky. Now, we take this object even closer to the mirror. It was infinity, beyond C, at C, between C and F, at F, and now between F and P. This is my focus, this is my center of curvature, and this is P. Right? Now they are saying keep the object between focus and pole, somewhere here, very close to the mirror. Now what will happen? Ma'am, one thing we know that ray will go parallel. Ray will go parallel and then it comes back, passes from focus. Till here, everything is true. Everything is true, right? But one important thing, now what else should we do? We can do the same thing, right? We can do the same thing, that now this goes here and it reflects back, comes back and passes from center of curvature. Now listen very carefully, very carefully. This row will continue going here. This row will continue going like this, and this row will continue going like this. Will they ever meet? Will they ever meet? No, because they are going away from each other. Here the distance was this, here the distance is so much big. So they are going away from each other. That means if rays are never meeting, the image will not be formed. True, the image will not be formed. But here is the trick part. What we do actually here, to make the image, we extend them backwards. But when backward, it's the mirror. Yeah, but in plane mirror also, remember, the image was forming on the other side of the mirror. The image was forming on the other side of the mirror. So here also, the image will be forming on other side of the mirror. So what we do, we extend this ray backward, we extend this ray backward, and wherever they meet, let me make it very carefully. Yeah. So wherever will they meet, we'll say that is where the image is formed. That is where the image is formed. So they are meeting at this point. They are meeting at this point, my friend. So at that point, the image will be formed. Done. Now this is the object. Now this is the object and this is your image. The image is being formed on the other side of the mirror. Now listen very carefully. Size, we can clearly see that it is enlarged, right? So object, when the object is between F and P, the image will be on the other side of mirror, or you can say behind the mirror. You can say behind the mirror. Done. Now, of course, the size is large. That can be clearly seen. But there is one thing very important. Here, we said that real rays were meeting. Real rays are meeting. Real rays are meeting. Rays are not meeting. But here, real rays are not meeting. Real rays are not meeting. We extended them backwards. We ourselves extended them backwards. So, these are not real rays. These are what? These are virtual rays. These are virtual reality. You have seen those games, right? Virtual reality. You wear a headset and you play. That is not there. It's a virtual world. So these rays, these dotted ones are actually not there. But we made it. These are the imaginary rays. These are the virtual rays. So we call it virtual. And if you see here, this is also not inverted. Yeah? Right? This is A, this is B. The ray goes and it goes at this point from A point. From here it goes and it comes back. If you extend it, the B point comes here. So it is not inverted. It is correct. So that's the word we call erect. So this image is virtual and erect. This image is virtual and erect. Done. So we are done with 6 cases of concave mirror. Let's see what were those. This was my concave mirror. This was my principal axis. This was the focus. This was the center of curvature. So object, let's say I name my object as, so first the object was at infinity. Second it was beyond C. Third it was at C. Fourth it was between C and F. Fifth it was at F. Sixth it was between F and pole. Done. Remember this. We know this, right? Let's see one more time. This was at infinity, beyond C, between C and F, at C, between C and F, then at F, then between at F and P. That is the same. So first at infinity, beyond C, at C, between C and F, at F, beyond F and P. Where the images are formed. Now look at it very carefully. This is lovely. Look at this. In the first case, at infinity, the image was forming at focus. So the image was forming at focus. At infinity, the image is at focus. Now beyond C, the image was between C and F. Beyond C, the image was between C and F. So this is beyond C, the image is between C and F. right? Then the third case, the image is object is at C, image is again at C. The object is at C, the image is at C. Then the object was between C and F, the image was beyond F. Between C and F, the image was beyond C, sorry. So the object is between C and F, the image was beyond C, right? Then at focus, our image was at infinity. When the object was at focus, the image was at infinity. And in the sixth case, the image was behind the mirror. So do you see the pattern? Is it hard to remember now? Is it hard to remember now? No, ma'am. You write the counting in the correct manner. You write the counting in the reverse manner at the exact positions. But one, this is infinity. This is beyond. Let me write it properly, okay? For you. You can make this diagram. This is a great trick. Nobody will tell you. This is beyond C. This is at C. This is between C and F, right? And this is at F, and this is between F and pole. Now look at that. First, the object was at infinity, the image was at focus. Beyond C, between C and F. The object was at C, image is at C. The object between C and F, the image is beyond C. The object at focus, the image is at infinity. And the sixth case is exceptional one, we'll remember that. Then, very easy trick, very great trick. Understood, everyone? So this is where we conclude our concave mirror. This is your concave mirror. You can take the screenshot if you want. Okay. Now let's move on to the, this is just the summary. The object is at infinity, image is at focus. Object beyond C, image between C and F. Object at C, image at C. Object between C and F, image beyond C. Object at F, the image is not formed. Object at, this is between F and P. F will be here. The object between F and P, the image is on the other side of the mirror. Then, okay, let's see what are the rules of image formation now for a convex mirror. Now for a convex mirror. Again, very simple, but here is a tricky part. In there, the image was real forming, right? The rays were actually forming. Now, let's see the rays are forming or not. First of all, understand that this concave mirror is a converging mirror. It is a converging mirror. What is the meaning of converging? That means all the rays are converging at a point, means meeting at a point. They are not going away from each other. In one case they are, but mostly they are meeting at a point, right? Mostly they are meeting at a point. So that is called converging mirror. On the other hand, convex mirror is called diverging mirror. On the other hand, convex mirror is called diverging mirror. That means the rays will go away from each other. They won't meet at a point. They will go away from each other. They will diverge out. Okay, diverge means they go away from each other. Okay, let's see. The first is the ray is coming parallel to principal axis. Same, and it diverges. It doesn't go like this. See, it diverges away. It goes away. So what we do? This is going away. We'll extend it back, just like the sixth case of concave mirror. Remember, we extend it back and we see that the point it is passing from is its focus. Is its focus. So again, the object is at infinity or parallel to principal axis. The reflected ray will go from focus. It will pass from focus, just like the concave mirror. But in here, it is a virtual ray now. It is a virtual ray now, not the actual ray, right? This is the virtual ray. The actual ray was this. It went away. Next, the ray is coming towards the focus. Towards the focus. If we extend it, it is passing from focus. So it is coming towards the focus. It is getting reflected back and it gets parallel to principal axis. So incident ray is towards focus. Towards focus. Right? And if we extend it, it is actually passing through focus and it reflects, and the image is then goes from, it is parallel to principal axis, just like concave mirror. Their actual ray was meeting. Here, virtual rays are meeting. Virtual rays are doing the work. Okay? Then it is coming towards the center of curvature, going away, following the same path. Following the same path, just like the concave mirror. And the last again, it is going, hitting the pole, diverging back, and these are incident ray and refracted ray. This goes back, this goes back. Okay? Understood? Now let's say how to form the image in this case. Now it's a very delight. There are only 2 cases of convex mirror, not 6. There are only 2 cases of convex mirror. First, the object, let's study this one. First, the object is at infinity. The object is very far away, right? Now, instead of using a concave mirror, we are using convex mirror. Object, the outside part of the mirror is reflecting, not the inwards. So, object is at 10 kilometers. The rays are coming and reflecting away from them. Okay, let's see. Parallel rays are coming. Parallel rays are coming. Parallel rays are coming. Now, instead of meeting like this, what? They are diverging away. Diverging away. So, you tell me, will these 2 rays ever meet? Even if you extend them any further, will they ever meet? They won't, right? So, we extend them backwards and we see that they meet at focus, right? So, image is now formed at focus. Done. Now, virtual rays are meeting, so it is virtual. And in case of convex mirror, the image will always be erect. It will actually always be virtual and erect. Done. So, first case is done. Second case, instead of all the points beyond C, at C, blah blah blah, there is just one point. At any point, wherever you kept your object, at any point away from the convex mirror, there is only one phenomena, one case that will happen. What? A ray will come parallel. A ray will come parallel and it will diverge out. It won't go like this. Remember, it will diverge out. We extend it back. It passes through focus. It passes through focus. Done. Another ray, it passes from center of curvature. So this ray goes towards center of curvature. Actually, it goes back. But we extend it back and this is where the 2 rays meet and this is now my image. So this is image and this was my object. So actually the object is at any point from the convex mirror, but the image, it will always formed between P and F. The image will always be between pole and focus of the convex mirror. And since it's on the other side of the mirror, real rays are not meeting, virtual rays are meeting. So it will be virtual and erect. It will be virtual and erect. Done? Understood? So we did all the image formation cases of concave mirror and convex mirror. Let's just look at their uses. Concave mirror is used in shaving and makeup mirrors because you want to see somewhat enlarged image, right? Now here you see convex mirror is never making a larger image. So whenever you need a large image, we will always use a concave mirror. Time sorted. Whenever you need a bigger or magnified image, we will always use concave mirror, right? So the headlights of vehicles, we use solar furnaces because we have to converge the light at one place, right? All that sunlight, we have to converge it at one place. So we need a converging mirror, that is my concave mirror. Then dentist mirror, again they need a bigger image of your teeth, right? And telescopes, again you want a light from a star to converge in your eyes. So we use concave mirror. Moving on to convex mirror, vehicle side mirrors. Now one thing you see that in case of convex mirror, you always forming a smaller image. A big truck is coming behind you and you want to see in that small image, small mirror, right? On your rear side mirror, your small mirror. So what will you use? You use an image, you use a mirror that will make a small image. right? And ma'am, I remember that concave mirror also forms small image in one case, but in concave mirror it was an inverted image. So your truck will look like this, and inverted truck is coming towards you. You don't want that. You want an erect image, right? Straight truck is coming towards you. So you want a shorter image and a erect image that is given only by a convex mirror. So you want a small image as well as an erect image of the truck. So that is given by your convex mirror. Then security and surveillance, road safety mirrors is always convex mirrors. Parking areas, in peepholes in those doors, that small mirrors in those doors, right? That is also your convex mirror. Sorry for that. That is also convex mirror. Then, so we know the uses of these two. Now again, a little bit of physics in this. All that was physics as well, but a little bit more. Now you have a mirror. Okay, there are two sides of the mirror, and we know that image was forming in this side as well in one case, and in this side as well in all the 5 cases of concave mirror. This is for concave mirror. So all the images, you have learned that x-axis, y-axis, right? So this is x-axis, this is y-axis. So the upper portion we take, the upper portion of y is positive, the lower is negative, right? The right side of the x-axis, is positive, but the left side of the x-axis is negative, right? Understood? The same we are going to use here. Any image that will be formed on this side. Okay, you have 3 things, that is u, your v, and focal length and radius of curvature that you need to take care of. U is your object distance. U is your object distance. Remember we saw that object is at infinity, so its distance will be at infinity. The object will be at C. So let's say the center, the radius of curvature is 50 meters. So the object distance will be what? It is at C, so it will be 50 meters. So this is object distance. V on the other hand is image distance. If the image is found between C and C is 50, F is 30, so we will say that image is somewhere between 50 and 30. Let's say it is at 35, so image distance is 35, right? This is focal length. We already studied this, and this is the radius of curvature. We already studied that. Done. Now come back to this. So any distance, be it object, be it image. This is my left hand side of the mirror. This is right hand side of the mirror. This is right hand side of the mirror, right? This is the upper portion, upper from the principal axis, and this is the down portion, right? Now see, let's take an example. In this case, let's see this one, okay? The object is above the principal axis, but the image is below the principal axis, right? So, how will you study this? Let's look at very carefully. All the distances. Now, my object was always placed on this side of the mirror, right? You remember? Every time we place the object on left hand side of the mirror. So, u, that is u, distance of object will always be negative. All the distances on the left hand side will be negative. All the distances on the right hand side will be positive. Just like the x-axis. This is positive, this is negative. This is positive, this is negative, right? The height above the principal axis, it is positive. The height below the principal axis, it is negative. This is, we are doing all for the numericals because this is a highly numerical based chapter. Okay. Now, done. That is it. So, distance. So, in 5 cases of concave mirror, you will see the object is always on the left hand side. The object is on the left hand side. The object is on the left hand side. Object is on the left hand side. Object is on at infinity but left hand side. In here the object is at right hand side. So now we know that for 5 cases the object is at left hand side. That means for the 5 cases, all those cases in which real and inverted image was formed, the image distance will be negative, because we know at left hand side image distance is negative. But in our sixth case, 1 to 5 cases, this one, in our sixth case, the virtual and erect image was formed on the other side of the mirror. That was my right hand side. So image distance will be positive. Done? Now, concave mirror focal length, it was on this side, right? We were studying on this side because this side is the reflecting one. This one is the shaded one. We have nothing to do on this side. We have focus on left hand side. So focal length will always be negative. If focal length is negative, radius of curvature is also negative. Now, height above the principal axis when the object was like this, right? Object was like this, so its height will be positive, but the image formed was down, right? Somewhere here. So the object image, the height distance below the principal axis will be negative. That is it. Let's see. For convex mirror, let's understand it better. See, this is left hand side of the mirror, all the distances will be negative. Right hand side of the mirror, all the distances will be positive. Above the principal axis, height is positive. Below the principal axis, height is negative. Right? Now, in case of convex mirror, let's see. In case of convex mirror, object is at left hand side. Right? Image is at right hand side. So here, object will always be left hand side. So object will always be negative. But image was here in this side. This side is my right side. Right side is positive. And we know for convex mirror, it is always virtual and erect. The image was always virtual and erect, right? So for virtual and erect, the image distance is always positive. I know it can be a little hard right now, but we'll do the numericals and you'll understand it. Just listen it carefully right now, so that when you go back, when you practice, you know that, oh, Aditi ma'am told this. Okay? When you understand this, it will be very clear. Okay? Then in here, we were using the focal length of this side, right? See, we were using the focal length of this side. Look at this. Right? So this is the right hand side. If this is right hand side, the focal length will be positive, because for right hand side, focal length is, every distance is positive. Right? Again, the radius of curvature, sine of radius of curvature will be equal to sine of focal length. Done? So this is positive. Height above the principal axis positive, below the principal axis negative. Done? This was all about mirrors. Anything? Yes, we are left with 2 things that we just need to revise. This is revision. Okay. So now first to 5 cases of concave mirror, the image was forming as real and inverted. It was real and inverted. Right? The size was all sizes. We saw point size, we saw smaller, bigger image, same size image, right? But the sixth case, we had virtual and erect image, and it was larger. Right? For convex mirror, 2 cases were there, right? Both of those cases we had virtual and erect images. And the size was always, you have to write always smaller, or you can write diminished, always diminished. So ma'am, somebody told you that the mirror is forming a virtual and erect image. How will you know? Concave mirror is also forming virtual and erect image. Convex mirror is also forming virtual and erect image. Now is where the size comes. You understand slowly why we are studying nature, size, position. Okay. So, in a concave mirror, the virtual and erect image will be there, but it is always larger. And in convex mirror, virtual and erect image is there, but it is always diminished. So, if you want diminished virtual and erect, you go for convex mirror. If you want larger virtual and erect, you go for concave mirror. Done? Done with that? Okay, let's move on to the next. We have a very important thing, that is your mathematics a little bit, that is your mirror formula. I told you this U is object distance from pole. This is your concave mirror, this is the pole, and let's say this is your object. So this distance, this is U. If the image is formed here, then this distance will be V. Right? And F is the focal length of the mirror. So 1 by F equals to 1 by V plus 1 by U. Let me make this diagram a little bit clear. This is your concave mirror. This is your principal axis. This is your pole. This is your focal length. This is your center of curvature. Right? Let's say your object is here. This is your object. So this distance from pole, this is U. Let's say this is your image. So this distance from the pole will be your image distance. Now let's see that this is the left hand side of the mirror, right? This is the right hand side. So in this case, U is, left hand side is negative. So U is negative in this particular case, okay? U is negative, V is also negative because it is also on the left hand side, and focal length is also on the left hand side. This is the focal length from focus to pole. It is also on the left hand side. So focal length is also negative. Understood now? Okay, so this is the mirror formula. You have to remember 1 by F equals to 1 by V plus 1 by U. We'll do the numericals, then you'll understand why we saw it. Right? One more thing is your magnification. Now we saw that image was diminished, image was larger, image was at same size. So that was the size of the image. Now how much the image was larger, how much the image was smaller, that will be given by the amount by which the image was smaller, larger, was given by magnification. We say it like this, that how much magnified the image is. Is it positively magnified, negatively magnified? Let's see what that means. So, first of all, the formula, that is height of image divided by height of object, and it is always equal to minus V. Minus is very important. Minus V is image distance, U is object distance. So, minus V divided by U. Understood? Here, M is obviously magnification. M is magnification, height of HI is height of image, HO is height of object, U is the distance of object from pole, V is distance of image from pole. Done? Now there are few things that you can remember. Now this is the magnification, right? If this magnification is greater than 1, if magnification is greater than 1, that means it's bigger. Basic common sense, right? That means the image is magnified. See, that means I'll tell you a little bit of math. M is greater than 1. That means height of image is by height of object. This formula, height of image by height of object is greater than 1. That means height of image is greater than height of object if we cross multiply it here with 1. So height of image is greater than height of object. That means bigger image. Right? That means magnified. Magnified means magnification, larger image. So if greater than 1, magnified. Less than 1, then this will be inverted, right? Height of image less than height of object, so that will diminished. If it is positive, then the image will be virtual and erect. If it is negative, then image will be real and inverted. And if it is plus 1, minus 1, then it is of same size. If it is equal to 1, if M is equal to 1, that means height of image is equal to height of object, right? So that means it is of same size. And if M is 0, that means it is point sized. Height of image is 0. So it is point sized. Let's see. Okay. Now, ma'am, magnification is plus 2. That means height of image by height of object is plus 2. So height of image is equal to 2 times height of object. That means height of image is double the height of object. So it is magnified. That we saw from more than 1, right? It is magnification is more than 1 plus 2. So it is magnified and we proved it as well. One more thing, see carefully. Okay, so minus V by U, we the formula of magnification is also minus V by U, right? So that is also equal to plus 2. That means V is equal to minus 2 into U. Understood? Let me write it carefully. Minus V equals to 2 into U by cross multiplying. So V will be, this minus I'll put here, minus 2U. That means the image distance is negative. The image distance is negative. That means the image is on left hand side of mirror. The image is on left hand side of mirror, right? The image is on left hand side of the mirror. And in which mirror the image is on left side of the mirror? In convex mirror, image was always on this side, right? That was right side. So that means this is a concave mirror. That means this is a concave mirror. One more thing you can do. This is negative. V is negative. That means magnification is plus 2. That means the image is virtual and erect. That means the image is virtual and erect. Wait a minute. Oh, wait a minute. See, one thing you have to take care of. This here, all we did was, let's do it again because I think there was a little bit of mistake. Now, V is negative, this is given. You have to be very careful that U is always negative because we saw in the sign conventions, right? U is always on the left hand side. We always placed U here, right? So always object was on the left hand side. That means U is always negative. That means here minus V will be equal to minus 2 into U. This gets cancelled. V equals to 2 into U. V equals to 2 into U. Now look at it carefully. This is magnified and V equals to positive. That means the image is virtual and erect. The image is virtual and erect. That means it can be a convex mirror, it can be a concave mirror. How will I see? But this is magnified. Convex mirror never forms magnified image. Convex mirror never forms magnified image. It always forms smaller image. That means it is this case, virtual and erect, and always larger, always magnified. That means it is a concave mirror. That means it is a concave mirror. Done? Great. Now you have to do with all of this. And one thing I'll tell you. For minus, whenever you see a negative sign, magnification negative, then you will have real and inverted, and convex mirror never forms real and inverted image. So the answer will be always concave mirror. Let me write it down. For magnification negative, it will always be of concave mirror. It will always be of concave mirror. If it by chance is positive, if the magnification is positive, then it can be either concave or convex. You'll have to see. Then you'll have to see the size. If it is bigger, then it is concave. If it is smaller, then it is convex. This is the size. Understood magnification as well. Okay, let's move on and do one very good question. Okay, an object 2 centimeter at height. So there is one rule in my class for numericals. See, physics numericals are a bit tough. You will get confused again and again. Now to remove that confusion, we have this rule. We write as we read. One line, we write as we read. So we read an object 2 centimeter height. Then we write, okay. So what is given? Let's write what is given to me in the question. In the question it is given that height of object is 2 centimeter. Right? We'll write with the units. Then place at a distance of 16 centimeter. Now object, that means object distance, that means U. It is placed at a distance of 16 centimeter. Now as soon as you get the distance, we know it is always placed on the left hand side, so it will always be negative. So as soon as you write object distance, you will write a negative sign with it. Then Then from a concave mirror, so you will write that it is given that we are dealing with concave mirror. We are dealing with concave mirror. Done. Now after this they are given which produces a real image. It is given that a real image is being produced. Now we know that concave mirror can produce virtual image as well. So it is given, they gave us that no beta, it is producing a real image. That means, oh, it is lovely. See, if it is real image, that means it will be on the left side of the mirror. It will be on the left hand side of mirror. That means your V will always be negative. So if in your answer you are getting a positive V, you should know that my answer is wrong. See how we understood that loop and we came back to that point. See? It is forming a real image. Real image is always formed on the left hand side. If it is always formed on the left hand side, the V will be negative. Done? Understood? Let's read it. What is the focal length of the mirror? We have to find what is the focal length of the mirror. So a bit of a tricky question because we just have U. Okay, let us write. To find, we have to find the focal length of mirror. We have to find the focal length of mirror. Yes, this is also given. Height of image. Real image 3 centimeter height. So height of image, I'll write like this. It is given as 3 centimeter. Now remember, there were two formulas. Let's just write it. There were two formulas. One was mirror formula. That was what? 1 by F equals to 1 by V plus 1 by U. Okay, ma'am, we can easily find focal length. But for that, you need V and U. You have U, but you don't have V. Right? So, one more formula we had. We had the formula of magnification, right? That was what? Height of image by height of object equals to minus V divided by U. Can I just pick up this part? Okay, let's see. I'll just pick up height of image by height of object equals to minus V by U. Right? Now I have U, I have height of object, I have height of image. Height of object, height of image, I have U. Can I find V? Okay, let's find V. Height of object is 2 centimeter, right? Height of image is 3 centimeter. Now here is the tricky part again. See, when it's a real image, that's why you have to remember all the cases. When this is a real image, that means if this is a concave mirror, it is formed on the left hand side, and we also know whenever the image was formed on the left hand side, it was formed below the principal axis. The image was below the principal axis, right? That means the height of image will be negative. So HI is not 3 centimeter, it is minus 3 centimeter. Understood? Is it difficult? Maybe you find it a little bit difficult, but understand it very carefully. There are lots of concepts piled up, but let's clear them, make clear notes and do this numerical ones. Okay, so height of image is now not plus 3, it is minus 3. Height of object is we always place object above the principal axis, so that is fine. Height of object is plus 2 equals to V we have to find, minus we will write as is, and U is again minus 16. U is always negative. See, we'll do lots of practice of lots of questions. Do not worry at all. You can either go check the channel as well how much practice we have done for the questions. So do not worry. At the starting you might find it difficult, but at the end you won't find it difficult at all. Okay, from here I'll just cross multiply these two. 3 into minus 16. Minus 3 into minus 16. And let's not cross multiply it. Let's just take this 16 here. Okay, minus 3 into minus 16 divided by 2 equals to minus V. right? So this 2 8s are 16. It cancels out. Minus minus plus 3 8s are 24. And this is minus V. So V comes out to be minus 24 centimeters. Units are very important. And U was minus 16 centimeter. Now see one thing. V was negative. And what we said? We said that V should be negative. Done. Now we can use mirror formula and find F, since we have V and we have U as well. Okay, let's do it. 1 by F equals to 1 by V plus 1 by U. So 1 by V is what? Minus 24, we just found, plus this is minus 16. Understand clearly how to write it. V was minus 24, right? Plus U is minus 16. So this will be minus 1 by 24 minus 1 by 16. Done? Done, everyone? This LCM we can take as 48. You have to practice your LCMs in math. The LCM can be 48. 24 into 2 will be 48. Minus 2 minus 16 into 3 will be 48. 16 into 3 will be 48. And this comes out to be minus 5 divided by 48. Now remember one thing. This is 1 by F. We have to find F. So we will invert it. We will invert it. 1 by F came out to be minus 5 by 48. So if we invert it, it will become F equals to minus 48 divided by 5, which will be 945 point, and this will be 3, this will be something around 9.6. So focal length will come out to be minus 9.6 centimeter. Again, one more careful thing. Focal length is negative, and the mirror that was given was concave mirror, and we knew that for concave mirror, wait for it, concave mirror, focal length is always negative. Done? Focal length is always negative. So you understood how we will do our numericals. It was a bit long. Maybe I should have chosen a different one, but it is easy. This one is over difficult. Let's see the other numerical, what it says. A convex mirror. So we are given that the mirror we are using here is convex mirror. Okay. Now, as soon as you write convex mirror, just write in the bracket that its focal length will be positive. Concave mirror, negative focal length. Convex mirror, positive focal length. So its focal length is positive. On an automobile has a radius of curvature of 3 meters. We have radius of curvature as 3 meters. Now I told you that radius of curvature and focal length are related. How? If you half the radius of curvature, that will give you focal length. So radius of curvature is equal to 2 times of focal length. So focal length will be R by 2. That means half of radius of curvature. This is also important. Remember this. Okay. Okay, the radius of curvature is given if a bus is located at 5 meters. Now a bus is located at 5 meters. That means bus is my object and object is U. That is 5 meters. And my friend, I know that U will always be negative. From the mirror, find the position, nature and size of the image. Here we have to find everything. Position, nature, that means real and virtual and direct. Position and size. If it's smaller, larger, how much smaller, what's the height? Okay, let's find it. Okay. So, my friend, from R, can I find F? F will be, this is the solution. F will be R by 2, right? So, F will be 3 by 2 meters. And since it's a convex mirror, F will be positive. So, it will not have a negative sign. It will have a positive sign. U is negative 5 meter. So, can I find V using mirror formula? 1 by F equals to 1 by V plus 1 by U. So 1 by F I have to find, 1 by F we have, right? F was 3 by 2 and U was, how much was it? U was 5 meter. U was minus 5 meters. So F is 3 by 2, right? And 1 by V we have to find, plus this is 1 by minus 5. Understood? This comes there, 2 by 3, and this is negative. If I take the whole term here, it will become positive, plus 1 by 5 equals to 1 by V. Now again, we can take the LCM as 15. 3 5s are 15. 2 into 5, 10. Plus 5 into 3, 1 into 3, 3 equals to 1 by 5. 1 by V. So 1 by V comes out to be 10 plus 3, 13 by 15. V comes out to be 15 by 13 meters. And this, my friend, is your answer. You can leave it in fraction as well, or you can keep it here 15 by 13, or you can solve it. But meters is very important. This was simple. This was simple, but you still need a little bit information about what are the signs and all. See, it is a convex mirror, and at convex mirror, very carefully, they are asking the nature. Nature you can tell without even solving, because we know that for convex mirror, the image forms is always virtual and erect. The image formed is always virtual and erect. Right? Now we have to find the size. Still, size of the image is not given. So if they ask size, you will find magnification. Okay? So let's find the magnification. Magnification is minus V by U. Right? So minus V. V is what? 15 by 13. Minus of 15 divided by 13. And U is what? U is minus 5. So this is minus 5. This, if you write, it will become 13 into 5. This will become 3. And these two minus will get cancelled. So this will be 3 by 13. Magnification will be 3 by 13, which is less than 1, right? That means it is a diminished image, because it is less than 1. Understood? Understood? So here, my friend, we are done with magnification. We are done with the reflection topic. Now let's move on to the refraction. Okay? Now you have definitely seen phenomena like this, right? When the head of someone looks bigger when they stand behind a glass of water, or you have seen the fish tanks, right? If you stand behind a fish tank and you look at the other person, they look a bit distorted, something like this. And if you go to pools often, you will see that when you go and take a dip in the pool, half of your body looks a little displaced. Now this might be an extreme case, but you know what I'm telling, right? It might look shorter, it might look fatter. What is all this? This, my friend, is the exact thing we call refraction of light. Now this is a kind of a word which you must have heard for the very first time. Reflection, you know, you talk about it every day. Oh, the light gets reflected, or this surface is a reflecting surface, or stuff like that, right? But refraction is something that is pretty new to you, and it is very important, where it is used mostly in lenses. Okay, and then those lenses are used at a lot of stuff, but we'll go through the basics of it. We'll understand what refraction is, we'll understand its laws, the image formation by different lenses, and all that stuff that we did in reflection, right? Okay, let us start. Now, what is refraction, ma'am? It is just a phenomena when light bends. Light does not reflect, we read light reflects. In refraction, it is a phenomena in which light bends when it travels from one medium to another. When light travels from one medium to another, it bends. Now, where it bends, that will study everything. Do not worry. Okay? Now, it is a phenomena of bending of light when it passes from one medium to another. Let's say this is my air. Above this glass is air, right? Now, above this glass is air, and inside this glass is water. So these are two different mediums. Air is a different medium, water is a different medium. So when light goes from air into the water, it bends, and that, my friend, is called refraction. I'll try to show you this in some short or some stuff, but it's a very, very, very important phenomena. Now what happens, we studied incident ray, reflected ray, normal in reflection, right? Here, instead of reflected ray, we will have a refracted way. Okay, now let's say this is my rarer medium. We'll talk about rarer medium and denser medium. Okay, so this incident ray is coming, right? And this is a different medium. Let's say this is water, behind this yellow line is water, above this yellow line is air. So it's a different medium. So this ray is going from air into the water. And you can clearly see that it should go something like this. It should go something like this straight if there was no change in medium. But it is bending. It is bending, right? So then we call it as refraction. Okay. Now let's look at some basics example of this where we see refraction in everyday life. Okay. So refraction, have you seen some fishes? You might have seen some ponds. You might have gone to some place where you see fish in water. Actually, what happens, this is a great concept used by fishermen as well. So a fisherman goes and there is this pond and is like, that is the fish I want to hunt. So there is the fish. Let's say this is the whole pond. This is the whole pond, right? This is the whole pond. And the fish, he can see that the fish is here. But actually, he knows that light is getting refracted. It is not going straight like this. It is refracted. So if you see that the light is coming something like this, if you trace it back, the fish is here. To the fisherman, it looks that the fish is at point A. But he knows that light is actually getting refracted. So this is the apparent position. But this position of fish is actual position. This is the actual position of fish. When light goes, when it goes from water into the air, instead of going straight, it bends towards the kid, right? But he knows, to him, it will look that the fish is here. The fish is at point A, but he knows that my father is a fisherman, so fish is not actually here. Fish is somewhat down. The actual location, the actual position of the fish is different than what I can see, right? Then there is this another example. You take a glass of water, go fetch a glass of water, put a pencil in that. Okay, pause this video if you want, put a pencil in that, and you will see that half of this pencil, something like this, half of this pencil will look something like this. Instead of a straight pencil like this, it will look that outside the air, in the air, the pencil is like this. But instead of going straight, it will look that pencil is broken in half and it got bent. It is due to refraction. We saw that light plays magic on our eyes, right? This is the exact magic it plays. Now, similarly, if you place a coin in a beaker, in a glass, you will see, it will look like the light is coming from water into the air, right? So it is bending. If I extend this, it will look like the coin is here. It is uplifted a bit. But actually the beaker is this deep. The coin should be here. But to us, it will look like that the coin is in here. It is a little bit uplifted. Right? Let us talk about a bit more of all the stuff that we are going to study in this. Okay? So there are two things. First, that a light, let's say, can go from air into water, right? And in other case, the light can go from water into air, correct? From air into water, from water into air. Now, if air, of course, we know that air is a bit lighter. If you try to walk in water, you can easily walk in air. But if you try to go and walk in water, it will be difficult, right? It will be difficult to pick up your leg and place it in the another position in the water, correct? That means water is denser. That means the water is a denser medium and air is lighter. So we say, instead of lighter, we say it is a rarer medium. In physics language, we call it rarer. That means here the light is going from rarer into denser medium. from rarer into denser medium, and here then it is inverted. It is going from water to air. That means it is going from denser into the rarer medium. Correct? Understood? Okay, very well. This is the basics of refraction, and we know that this was, let's say, this is my air, correct, and this is the water. Very good. Now a ray is coming. A ray is coming. Let me change the color. Yes, now it's visible. Okay, so a ray is coming. Now technically it should go straight like this. Technically it should go straight like this. It is straight, almost straight, yes. So technically it should go straight like this. But if we know that it is changing its medium, so it will bend. Now the point comes, when the light goes from denser to medium or rarer to denser medium, we also know one more thing, that is that we draw normal. We always draw normal. So even in the reflection part, we know that at the point of incidence, we drew a normal. Right? So this is the normal. This is my incident ray. This is my refracted ray. Not refracted ray. This is normal, and we'll draw the refracted ray. This diagram is clear. Now, if the medium is rarer and this one is denser. So if the light is going from rarer to denser, it will bend towards the normal. It will bend towards the normal. So actually the ray will go something like this, and this will be your refracted ray. Understood? Understood? Now let's make the same diagram, but this time the ray is going from denser, the ray is going from denser to rarer medium. Let's see. Now this medium is denser. Let's say that is water. Let's say that is water, and this is a rarer medium. That is my air. Correct? Now if the ray is going, it is incident. Correct? Then I'll draw a normal. You have to go through it step by step. Okay? You'll draw a normal, and then again, according to my clarity, it should go straight. Something like this. But since the medium is changing and now it's denser to rarer, it will go away from the normal. It will go away from the normal, and this is your incident ray, this is your normal ray, this will be your refracted ray. So what do you understand? If a ray is going from one medium to another, it won't go into a straight path, it will bend somewhere, but it will bend. Now, if it is going from rarer to denser, then it will bend towards the normal. It will bend. This is a very important point. That's why I'm giving it so much time. Okay, it will bend towards the normal. It will bend towards the normal. Understood? But if it is going from denser to rarer, this is denser to rarer, then it will bend away from the normal. It will bend away from normal. Understood? If the light is going from rarer to denser, it will bend towards the normal. If the light is going from denser to rarer, it will bend away from the normal. It will bend away from the normal. This is my normal, right? Now, this will be my incident angle. This will be my refracted angle. And now angle I will not be equal to angle R. Understood? And one more very important thing. When the light is going from rarer to denser, you can clearly see that the angle R is smaller than angle I. Right? So here, angle R will be smaller than angle I. Understood? Make sure you are taking the notes of this, or at least take a screenshot, because this is a very important slide. It will form your basics. Now from denser to rarer, it will bend away from the normal, and here you can see this is my angle of incidence and this is my angle of refraction. So it is definitely bigger than angle of incidence, right? So here angle R is greater than angle I. Understood? This is from denser to rarer. Okay, and the previous one was rarer to denser. This is my case of rarer to denser. Understood? This is basically the basics of your refraction. That is it. Okay, let's quickly see some of the very important topics. The first one is laws of refraction, just like we had laws of reflection. The second law of reflection said what? The incident ray, the reflected ray and the normal all lie in the same plane. This is similar for laws of refraction as well. The first law says that the incident ray, the refracted ray and the normal to the interface. Now interface is a boundary. It is a boundary of two mediums. Okay, boundary of two mediums. So the interface of two transparent media at the point of incidence, when the light is going like this and this is normal and this will bend. So at this point, the point of interface of two transparent media at the point of incidence, everything will lie in the same plane. Understood? Now next law is basically very simple. Now we knew in reflection we had the relationship that angle I is equal to angle R. But in refraction we know that is not the case. Angle I is not equal to angle R. That is refracted angle, right? So what is actually the relation? The relation actually is, if this is my media, this is the incident ray, normal, and it bends towards. So this is the incident angle, this is the refracted angle, this is normal. Correct? So what is the relationship? Relationship is sine of angle of I. You will study sine and cos and tan theta all in trigonometry in mathematics. For now, just remember that sine of angle I divided by sine of angle R. Divided by sine of angle R is always constant. It is always constant. This is your second law of refraction. Second law of refraction. Understood? Very easy. This is your second law of refraction. Let's read it. The ratio of sine of angle. The ratio of sine of angle of incidence, that is your I, to the sine of angle. To the sine of angle of refraction. Refraction is always constant for the light of a given color and for the given pair of media. That means for air and water, it will be constant. But if you change it to air and glass or glass and water, it will be different. Okay? Understood? Okay, let's move on. Okay, this is also called Snell's law. Remember this? This law is also called Snell's law. Understood? Okay, let's move on to the next topic. We have the refractive index. Now I told you that light will bend, but how much will it bend? That is a question. That is a question that can come into your mind, and if it did, then great. You are some of the prodigies out there. So, what is refractive index? Refractive index is the extent of the change in direction. See, this light is incident. Technically, it should go straight. But this is the extent. This is the extent it bended. It got bent towards the normal. Right? If the light was bent right here, so it is more bent. Right? If it's here, it is more bent. If it goes like this, it is less bent. It is less bent. Right? So the extent with which the direction of incident ray got changed is decided by the refractive index of the material. See, the extent of the change in direction of the ray of light that takes place in a given pair of media may be expressed in the terms of refractive index. So the value of refractive index tells us that how much the light will get bent. Let's say the value of my refractive index is 1 and value of refractive index is 2, value of refractive index is 3. Now what will happen? What will be the difference? In here the light will go straight actually, because there is no difference. Refractive index is 1. But in here the light will bend slightly. It bends slightly. And in this one, the refractive index is too much. The light will bend too much towards the normal. Understood? Can you clearly see the difference? So this is what refractive index tells us, the extent by which this light is changing its direction. Understood? Now, what it depends on? It depends on the velocity of light in the medium. See, N21 is what? N21 is the refractive index of medium 2 with respect to medium 1. So you can write whenever you see N21, N and in its foot, it's written N21. You can write N2 divided by N1. I know it's getting a little bit heavy on the physics side, but it's okay. Do it very easily, very calmly. You'll understand it properly. N21, you can write it N2 by N1. Now this is equal to V1 by V2. That is the inverse of this, right? Okay. Let me I'll ask you that will the light go with more speed in water or in air? It will go with more speed in air, ma'am. Definitely, because water is denser, right? Now, if water is denser, that means that refractive index is more. See, if let's say the example of water and air. Correct? The refractive index of water will be more than the refractive index of air. The refractive index of water is more than refractive index of air. Why? Because water is denser than air. Water is denser than air. Let's write it. Density of air. And here the density of water. Understood? So the density of water is definitely more than density of air. That means the refractive index of water will be more than refractive index of air. If the water is denser, obviously the light will get some difficulty passing through water, right? Because there are so many, density means there are so many molecules in one place. In air, there are gas molecules scattered all around, but we have space to move around those gas molecules. But in water, the hydrogen, oxygen molecules are so packed together that we face difficulty passing through that. And similar is the case for light. My speed is more in water or more in air? Of course in air, right? So similarly is the cases for light. So for light, the speed will be less in water and more in air. The speed of light will be more in air than water, just like the speed of Aditi ma'am. Correct? So my speed will also be less in water than in air. Done? Understood? Now you understood? Let's come back. Okay. So N21, that means it is inversely proportional. See, in which the medium which is denser has less speed. The medium which is rarer has more speed. That means refractive index we write it with as the symbol N. Okay, we write it as N. So instead of R, let me write it here N. That means if the speed of light is less, then the refractive index is more because density is more. Understood? Okay. So that means these are inversely proportional. So N2 by N1 equals to V1 by V2. Understood? Very clear? Okay. So this is simple. V1 is the speed of light in medium 1. V2 is the speed of light in medium 2. That means if N2 is more, V2 is less. Understood? The refractive index is more, speed is less. Very clear? Very basic? Okay. Now there is one thing called absolute refractive index. Now everyone, we know that when light comes from sun to the earth, inside that whole space, it's just vacuum. Right? It's just vacuum. That means no gas molecules, no water molecules, no dust particles, nothing. Not even oxygen, not even air. So for between sun and earth, there is only vacuum. There is only vacuum. Okay? Now in earth, we take it at earth, or especially in class 10th physics, we take it similar to air. In most cases, we take it similar to air. So absolute refractive index is how much the extent of light will bend when it goes from one medium when it goes from vacuum into the another medium. What we thought in refractive index, it will go from one medium to another. That medium can be glass, water, air, your kerosene, oil, anything, right? But absolute refractive index is, let's say they are saying absolute refractive index of kerosene oil is 1.5. This is just an example. That means the light is going from a vacuum into the kerosene oil. Okay, that means absolute refractive index. That means alone if you want to calculate the refractive index of something, just one thing, that is water, that is air, that is glass, then you will say its absolute refractive index is 1.52, whatever the value is. Done? So when the light is going from either air or vacuum into the water, then it bends at this angle. So the refractive index of water is 1.5. Now this is, my friend, is the absolute refractive index. It is the absolute refractive index, that is refractive index of water with respect to vacuum or air. Done? Okay, now we are moving on to one very important topic. This will come in the exam 100% sure. Okay, any question, some question will come in exam from this question, that is your glass slab. Now you have seen glass slab in your labs, in your school. They must have shown you a glass slab. So glass slab is nothing but, let's say this is my phone, it is somewhat thick, right? So glass slab is similar to this. It is thick, but instead of made up from any other material, it is made up of glass. Understood? It is made up of glass. Now we have to see what will happen if the light goes into the glass slab. So glass slab is this thick. Light will go, now light is in air. Then light enters glass. Now it comes out, so it is again in air. So there are two refractions happening in glass slab. First of all, there are two refractions happening in the case of glass slab. Understood? Now let's see how it's done. First of all, this is air, then this is glass, then this is air. So air is a rarer medium, glass is a denser medium, and air is again a rarer medium. So in the first case, in the first boundary, this is my first boundary. So first refraction, light is going from air into the glass. That is, light is going from air to rarer to denser medium. If light is going from rarer to denser medium, it will bend towards the normal. When light is going from rarer to denser medium, it will bend towards the normal. This is my incident ray. It got incident at this surface, and instead of going straight, it bends towards the normal. And now this is my refracted ray. Understood? Clear? Very simple. Right? Next, now in this refracted ray tries to come out of that glass slab. Right? It needs its freedom. So it tries to come out of that gas slab. But now this medium is denser medium. Here it was going from rarer to denser. Now this refracted ray will be going from denser to rarer medium. Now ma'am, in denser to rarer medium, the light will bend away from the normal. It will bend away from the normal. So instead of going straight like this, it went away from the normal. Understood? It went away from the normal. Now this ray is called emergent ray. This ray is called emergent ray. Incident ray, refracted ray, emergent ray. Understood? So the actual path of light, what we saw, the actual path of light becomes what? This is the incident ray. Now instead of going straight, it bends towards this, and instead of going straight, it bends away from the normal. This is the path of light that we will see coming out from the glass slab. Understood? Now tell me one thing. There are 2 to 3 things to remember in here. First, the incident ray, the incident angle, and this will be the emergent angle, right? With the normal. The emergent ray that makes with the normal is called emergent angle. So incident ray and emergent incident angle and emergent angle are equal. In ideal cases, they should be exactly equal. But when we do the experiment, this is your experiment is there in your 10th class. Okay, so make sure you do it properly. So they will come out almost equal. Almost equal. They should come out almost equal. Right? The first case is that. Now, one more thing. This incident ray and this emergent ray. The incident ray and emergent ray. These rays are parallel. Incident ray is parallel to the emergent ray. Understood? Incident ray, if you extend it backwards, if you extend this emergent ray backwards, or you have extended this emergent ray, so you will see that the emergent ray, this emergent ray and the extended incident ray, these two are parallel to each other, and the distance, the shortest distance between them, this D is the shortest distance between emergent ray and the extended incident ray. This is called lateral displacement. Lateral displacement means the whole ray got shifted like this, right? It should go like this, but the whole ray is just shifted. It didn't tilt. It just whole ray got shifted downwards. So that is called lateral displacement. So our D is the lateral displacement. Understood? Let's see, let us write the refractive index formula for this. Okay, so speed of light or speed of this, yes, light is V1 and let's say it is V2 in glass and then it will be V1 again in the air, right? And let's say the refractive index is N1, this is N2 and again this will be N1 because these both are air, right? So what will be the refractive index? N1 or N2 divided by N1, and you have to write it like this. This is the refractive index from 1 to second medium, right? So this will be, now of course the velocity of light will be slower in glass than in air, so it will be inverse. This will be V1 divided by V2. N2 divided by N1 equals to V1 divided by V2. That means N of glass divided by N of air will be equal to velocity in air divided by velocity in glass. Understood? Okay, great. Now we are done with most important topics and we are moving on to another most important topic. We studied spherical mirrors, so we'll again study spherical lenses. What is the difference between mirror and lenses? See, you stand in front of a mirror in the morning and you're doing your makeup. Okay, so that is showing your image. But you go out and you stand in front of a glass door. You don't see your reflection. You see the other side of the mirror, right? If someone comes and stand behind your mirror, you won't be able to see them. You will be seeing yourselves. But if someone comes and stand in front of, on the other side of glass door, you will be able to see that person, right? You will be able to see that person. So that glass door is a lens. Your mirror is your mirror. So lenses let the light pass through them. Lenses let the light pass through them. On the other hand, mirrors don't let the light pass through them. They throw it backwards. Okay? Okay, now let us see there are two kinds of mirrors. Similarly to lenses, we have concave lenses. Similar to mirrors, we have two lenses, concave lenses and convex lens. Okay, now very important, concave lens is thicker on the edges. It is thicker on the edges, but it is thinner in the middle, right? And this is inverse. This is thinner on the edges, thin edges, but thicker middle. This is thick from the middle. Done? Understood? Just remember, this is convex lens. This is thicker from the middle. It is like this. That is convex. Concave on the other hand, it is thinner from the middle and thicker at the edges. Understood? Now, we studied in the mirror. This is a very important point. Listen it very carefully. In the mirrors, we knew that we have two mirrors. We have concave mirror and we have convex mirror, right? These are mirrors. These are mirrors. Done. Now in concave mirror, the concave mirror was converging mirror. The concave mirror was converging mirror, and the convex mirror was diverging mirror, because concave mirror was letting the light meet at a point. It was converging the light rays. Convex mirror on the other hand was diverging the light rays. Let's see for lenses. Now everything you will see in lenses will be opposite of that of mirror. What I'm trying to tell you, that in here concave was converging, but in lenses convex lens will be converging lens. Okay, and in lenses concave lens will be diverging lens. Understood? Concave converging, but in lens convex is converging. Convex diverging, but in lenses concave is diverging. Then we'll see it through the diagrams as well, but understand this, take it in your brain for some time. Okay. Okay, so concave mirror is diverging lens, concave lens is diverging lens, convex lens is on the other hand is converging lens. Okay, in mirrors concave was converging and convex was diverging. Understood? Understood? Remember the shape. Concave mirror looks something like this, thicker from the edges, thinner in the middle. Convex lens looks something like this, thicker in the middle, thinner from the edges. Done? Okay, let's move on to understand some of the basic concepts of lenses, just as we did in mirror. There was center of curvature, focus, pole, and focal length, radius of curvature, all that stuff. Here also is almost the same, but instead of center of curvature, we write 2f. We knew, right, that R is double of f. Right? So in here, instead of giving it as a name R, we let it write as 2f only. Okay, we let it write as 2f only. So see, this is my f1, this is my 2f1. Right? This is my f1, this is my 2f1. This is a convex lens, this is a concave lens. But both the side of lenses are refracting, because when you saw a glass slab, both the light was going into the glass, coming out. Similar is for the lenses, right? It is just a glass slab, but just of a different shape and different structure. In here the light will go, this is the first surface, it will go into the glass, this is the second surface, it will come out. Right? So this other part is also curved, right? So it will also has its own focus, it will also has its own 2f. So this will be called f2, this will be called c2 or 2f2. We will call it 2f2. Okay, 2f2. NCERT calls it 2f2, we will call it 2f2. F2, everything is similar for both the lenses. Okay, this is f1, f1, f2, f2, 2f2, 2f2, 2f1, 2f1. Just the shape of the lenses is different. Understood? Now let's move on to another important topic. I have said it a lot this time, right? Important, but these are important. So let's move on to the next topic, that is image formation by lenses. This is a lens that I'm wearing. Now, you know how important this is for me. I won't be able to say it with say the word without it. Okay, so that is why we have to understand lenses, how lenses work, how the image is formed using that lens. Okay, the image formation first by convex lens. Now what did I tell you? Everything in lenses will be opposite of the mirrors. In mirrors, concave mirror has 6 cases. In here, convex lens, concave mirror had 6 cases. In here, convex lens will have 6 cases. Understood? So the first case is my object is at infinity and all the cases are similar to mirror. The object is at infinity, beyond C, at C, between C and F, at F, between F and P. Everything is same. Even the place where the position where the image will be formed, that is also same. Okay, but just the image won't be forming on the same side. It will be forming on the other side of the lens, because lens won't reflect, it will refract. Okay, so all the rays are coming parallel. It will meet at a point called F2. Right? So the image is formed at F2. Again, everything will be similar to concave mirror. There in concave mirror, nature of image was what? Real and inverted. So here the nature of image will be again real and inverted. Real and inverted. Done. And the size of the image, we can clearly see the size of the image will be point sized. It will be point sized image. Object is at infinity, image will be at focus, nature will be real and inverted, size will be point sized. First case of convex lens. Image formation by convex lens or refraction by convex lens. Because anyways, these lights are bending after going through a lens. That is refraction. Right? Okay, let's move on to the second case, that is beyond 2f2. We had beyond C, here we are calling C as 2f1. This side is f1, that side is f2. Right? So here you can see object is beyond 2f1. Clearly visible. Now one ray will go parallel, one ray will go parallel, passes from the focus. This is clear. One ray will go parallel, passes from the focus. Now, remember the rules of mirror. When the ray was hitting center of curvature, it reflects back, traces the same path. Here is one more thing that I actually forgot to tell you was this center point. The center point, it is called optical center. It is called optical center of the lens. Now, whenever the ray is passing through this optical center, it won't have any refraction. It won't bend this or it won't bend here. It will go straight. As it came, it will follow the straight path. Okay. So, first ray is coming parallel to principal axis, bends and passes through focus, just like the mirror. Another, instead of center of curvature, it is passing from optical center and it is not showing any refraction. And then it meets the another ray and it meets between F2 and 2F2. So the image is formed between F2 and 2F2. See, I made all the ray diagrams in the form of mirror, right? In lenses, it is similar. So I'll be showing you the already made diagrams, but it is very clear, right? One ray is coming parallel, the object is beyond 2f1. One ray is coming parallel, passes through focus. Another ray passes through optical center, goes straight. Wherever these two rays meet, there will be my object. Understood? Now here also the nature was what? This is a convex lens. That means the nature will be similar to concave mirror. It will be similar to concave mirror. This is actually a convex lens. Its nature will be similar to concave mirror. Correct? Nature was real and inverted. And you can see, ma'am, the real rays are meeting. They are passing through the lens and real rays are meeting and the image is inverted. So it is real and inverted, and size, my friend, will be smaller, or you can write diminished. It will be a diminished in size. Okay? Diminished or bigger? Yeah, it will be diminished in size. Okay? Done? One more thing you can remember from the size was, in the first case it was point size. We got the object a little closer to the lens, the image will get a little bigger. Then at C, in the case of mirror, the image got same size. Then when between C and F, the image got bigger. And then even it went to infinity with an enlarged size. So as we bring the object closer to the mirror or the lens, the image keeps getting bigger. So in the second case, it will be bigger than point size, but still smaller than the object. Done. Then moving on to third case, at F1 similar, at 2F1 similar to at center of curvature. Okay. Done. So this will be at 2F1. Again, one ray goes parallel, one ray goes from the optical center. The ray that goes parallel bends and passes from focus. It bends and passes from focus. Let me see. This is how you have to make it. It goes parallel, then it bends and passes through focus. Understood? Another ray goes through optical center. That's why it is very important to use scale. You don't have this kind of technology with your pen and pencil right now that you can make clear lines, right? So this is where it is being made, and this will be my image that will be at same point where the object was. The object was at 2f1. The image will be also at 2f but 2. This is 2f2. If you wrote 2f1, that will be wrong. This is 2f2. Again, the nature will be what, my friend? The nature will be real and inverted, and size now will be same size as that of object. Same size as that of object. Understood? Okay, next case we brought the object even more closer between 2f1 and f1. Between 2f1 and f1. Now one ray will again go parallel. It will pass from the focus. It will pass from the focus. Another ray passes straight from the optical center, and it meets the another ray at this point. This is the optical center, and now this is my image, which is clearly visible. It is very, very enlarged. Right? So the image position is beyond. What happened? The image will be beyond 2f2. The image position is beyond 2f2. This is my image. Understood? Okay. So the nature here will be real and inverted, and the size will be enlarged that we can clearly see. Understood? We can clearly see. Next case is now we got the object a little more closer, and the object is now at f1. The object is now at f1. So the object is at f1. Again, one ray will go parallel. It will pass from the focus, right? It will pass from the focus. Another ray will go into the optical center and will pass without any refraction. And see, these two rays are now parallel. Similar to the case of mirror. These two rays are now parallel, and hence they won't ever meet. So the image, according to new NCERT, will not be formed, right? Or you can say that the image will be formed at infinity. In that case, you can write that the image is real and inverted. It's extra large in size, extremely large. Okay. But according to new NCERT, the answer is image will not be formed. Okay. Done. Now comes the sixth case, just like concave mirror. We know the concave mirror had its sixth case where it was an exception. So let's see the exception in the case of lens between f1 and O, between f1 and optical center. Correct? Now this is the focus. It is placed between f1 and optical center. One ray will go parallel and it will pass from the focus. Just as before, it will pass from the, I think you are not able to see this line, principal axis, right? Let me just... Yep. So the ray is going parallel and it's passing from f2. Okay, this is your f2, right? Another ray goes into the optical center and these two rays are again diverging. These two rays are going apart. They are not converging at a point. They are going apart. So what we do? Just like in the case of concave mirror, we extend them backwards and we see they are meeting at a point. They are meeting at a point at here. So this will be your image. Now, in this case, you'll have to write the image. The image will be formed beyond f1 on the same side of lens. Understood? Image will be formed beyond f1 but on the same side of lens. Sorry, beyond 2f1. Beyond 2f1. The image will be formed beyond 2f1 on the same side of lens. Understood? But in this case, real rays are not meeting. So the image will be virtual and erect. Can you see? This is exactly the same case of concave mirror. The sixth case, the image was virtual and erect. It was not meeting on the same side of the mirror. It was forming behind the mirror, and the image was extremely large. Here the image is extremely large. Here the size is large. Again, done. So we are done with 6 cases of convex lens. How quickly we did it? Because we did the mirror cases very calmly. Right? So that is the key. First you do the things very calmly, understand it properly, and then you will pick up the pace. And you don't have to pick up the pace at this point of time. We have the whole year. We'll study it completely, very, very properly. Do not worry. I'm here. Okay? Okay. Let's next move to concave lenses. Now this is my concave lens. Again, just like convex mirror, it has just only 2 cases. When the object is at infinity, now this is a diverging lens. This is a diverging lens. So the rays will not be meeting at a point. In case of convex lens, see, rays are meeting at a point. Right? But here the rays are not meeting. They are going away from each other. So we have to extend them backwards. When we extend them backwards, we see that they are meeting at a point which is the f1 of my concave lens. So when the object is at infinity, the image will be formed at, now in this you have to write at f1, not f2. In the convex lens case, we wrote that the image is being formed at f2, right? See. In this case, we wrote that image is at f2. But in the case of concave lens, we are writing that the image is at f1. Understand the difference? And just like convex mirror, it will have virtual and erect image. It will form virtual and erect image that you can clearly see it's a virtual because real rays are not meeting. Virtual rays are meeting. So the nature will be virtual and erect. Done. And the size is point sized. Understood, everyone? Okay, let's move on to the next, another case, just the last case. Okay, in here we have an object. You can place it anywhere between the optical center and infinity, but we have placed it between 2f1 and f1. Okay, so if you place it between 2f1 and f1, what will happen? Similar case, one ray will go parallel, but in here it is not converging, it is diverging. It will go something like this because it's a concave lens. It is a concave lens and that is diverging. Correct. So it will go away. It will diverge. Now if we extend it backwards, and another ray will move through optical center. So these extended one and this real one will meet at a point, right? So this will be my image. And in this case, image will always be formed between optical center and f1. Not f2, f1. Understood? And that is it. And we know just like convex lens, we have virtual and erect image in this case as well. Virtual and erect, and this is diminished, that we can clearly see. Understood, everyone? Any doubt? Right? Okay, so image is between O and F1 and it is virtual and erect and it is diminished. Now let's just quickly see what kind of images we formed. For convex lens and for concave lens. In case of convex lens, now this is similar to concave. I'll write very little so that you don't forget. It is similar to concave mirror and this is similar to convex mirror. The the nature of image formed by both mirror and lenses of two different sizes will be of the same. Okay, let's see. For convex lens or for concave mirror, we have 6 cases, right? For first to 5 cases, the image will be real and it will be inverted. Okay, and it will be of all sizes, so it will be of all sizes, correct? Both for lens and mirror. For the 6th case, however, for 6th case, the image will be virtual. The image will be virtual and erect, right? And it will always be large. It will always be large. On the other hand, for concave lens or convex mirror, we just have 2 cases, right? And in both the cases, the image will be virtual and erect, and it will always be diminished. Understood? Now you can clearly see the difference where convex lens, concave mirror are similar, concave lens and convex mirror are similar. In here we have 6 cases, first 5 cases real and inverted image, all sizes, 6th case virtual and erect, large image. But for convex mirror or concave lens, we have only one kind of nature of image, that is virtual and erect, and it will be always be diminished. And you also know that if you get a virtual and erect image, you will ask the question that is it larger or is it smaller? If they say it is smaller, then it is that case concave lens and convex mirror. If it is larger, then it is concave mirror or convex lens. Understood? Then you can take the screenshot of this page, very important, and that is it. We are done with all the optical instruments. We did glass lab, we did lenses, we did mirrors, where we did 2 kinds of mirrors, 2 kinds of lenses, and all that is it. There is, however, one more thing that is left in this whole chapter. First, again, let's look at the sign conventions, just like we did in mirrors. So, everything is same. Left hand side, distances are negative and U is always placed on the left hand side. However, right hand side, distances are positive. Upside on above the principal axis, the height is positive. Below the principal axis, height is negative. Understood? And for concave lens, now for concave lens, remember the images were being formed on left hand side of the lens. Can you clearly see? The image is formed on the left hand side of the lens. That means we will be negative. For virtual and erect, in case of lenses, we will be negative. U is always negative, right? Now focal length of concave lens, concave mirror. Wherever you see a concave word, the focal length is always negative. Either for lens, for mirror, focal length is always negative. So radius of curvature is also negative. Height above the principal axis positive, below the principal axis negative. Now coming on to convex lens, again left hand side negative distance, right hand side positive distance, correct? So above the principal axis height is positive, below the principal axis height is negative. Now U is always placed on the left hand side, so U is negative. In case of convex lens, all the images were formed on the right hand side. In the first to 5 cases, the image was formed as real and inverted. Right? So that will be positive because real and inverted image was formed on this side of the lens. For virtual and erect, 6th case, we saw that image was being formed on the left hand side, a big image was formed on the left hand side. So for virtual and erect, the image will be negative. Understood? Again, focal length of convex lens and convex mirror both are positive, and height above negative, height above positive, height below negative. Right? Now, let us, okay, so we are left, just like we had mirror formula, we have lens formula. And it is almost similar. The only difference is 1 by F. In mirror formula, we had 1 by V plus 1 by U. Right? But in here, we will have, this is a little bit wrong, let me correct it. We have 1 by V minus 1 by U. For mirror formula, we had 1 by V plus 1 by U, right? But in here, we will have 1 by V minus 1 by U. 1 by V minus 1 by U. Understood? This is your lens formula. This is your lens formula. Done? Again, F is the focal length of the lens, V is your image distance, and U is your object distance from the optical center. Understood? Now similarly, we had magnification. In here we are also having different sizes of images, correct? So magnification in mirror, it was minus V by U. In lens it is plus V by U. In lens it is plus V by U. It will be same, M equals to height of image divided by height of object equals to V by U. Till here mirror is also same, but in mirror we had minus V by U. In here we'll also only have V by U. Okay, moving on to next, let's do a question quickly. Okay, let's do a quick question. The first question says a concave lens has focal length of 15 centimeter. So let's write it. What is the rule? Ma'am, in Aditi ma'am's rule, we have a rule that as we read the question, we write what it is given in the question. So it is given that a concave lens is there. So I will write concave lens. And with my knowledge, I know that focal length of concave lens, anywhere where concave comes, focal length is negative. So I will just in the bracket write that focal length will be negative. Just now, for my convenience. Okay? Now they have said that focal length is 15 centimeter. Now I know that focal length is 15 centimeter, but since it is negative, I will put a negative sign in front of 15. Okay? At what distance should the object from the lens be placed so that it forms an image at 10 centimeter? So they are asking where the object should be placed. So we have to find U. We have to find U, that is object distance, where the object should be placed when the image is at 10 centimeter. But image is given. Image is at 10 centimeter. Now you have to use a little bit of your brain. Since it's a concave lens, ma'am, concave lens, it has just only two cases. In both the two cases, this is how you think. You think of concave lens, okay, two cases. In both the two cases, the image was virtual and direct. In both the two cases, the image was formed on the left hand side of the lens. The image was formed on the left hand side of the lens. That means there will be a negative sign in front of concave lens. That's why we studied sign convention, my friend. In case of concave lens, the image distance will be negative. I told you. Okay, because the image was forming on the left hand side of the lens. So V will be negative. All this, why students think light chapter is difficult? Because they don't go through it with the right approach. They don't go through the questions step by step. You have to think concave lens, okay, focal length is negative. That's it, clear. So read the whole question. Now go. Okay, concave lens, only two cases are there. If it was convex lens, 6 cases were there. Real and inverted and virtual and direct. So V is different, sign of V is different in both cases. Okay, leave that. For now, it is concave lens. We have two cases. In both the two cases, the image was formed on the left hand side of the lens, and for left hand side we take distance as negative. So V will be minus 10 centimeter. Now I have F, I have V, I know the lens formula. Can I easily find U? Okay, I know the lens formula is what? The lens formula was 1 by F equals to 1 by V minus 1 by U. Now 1 by F is given, that is minus 15 centimeter. So this is minus 15. 1 by V is also given, that is minus 10, right? So this is minus 10. Minus 1 by U I have to find. Can I clearly solve it? Right? So this is minus 1 by 15 equals to minus 1 by 10 minus 1 by U. Now in all these cases you learn in math, you have learned in maths that you can cancel this negative sign from everywhere. Right? You cancel this negative sign. Now 1 by 15, this 1 by 10 is positive now. It will come here, it will be minus 1 by 10 equals to 1 by U. Right? You will take the LCM of this. You will take the LCM and that will be 30. Okay. So 15 into 2 is 30. So 1 into 2 is 1 into 2 is 2, and minus 10 into 3 is 30. So minus 1 into 3 is 3. That is 1 by u. So this will be minus 1 by 30 equals to 1 by u. So if you reciprocal, it will be minus 30 centimeter. And from here we know our answer is right. Why? Because u is always negative. U is always placed on the left hand side of the lens, right? So u is always negative. So our question is correct, and this is your correct answer. Okay, one more thing they have asked is also find the magnification produced by the lens. Now I have V, I have U, I also found U, right? That is minus 30 centimeter. This is the answer. So can I easily find a magnification? Magnification formula was given by plus V by U for lenses. Now V is what? V was minus 10 centimeter. V was minus 10 centimeter and U is minus 30. Never forget the sign. Minus 10 divided by minus 30. This cancels out. So M comes out to be 1 by 3. Now 1 by 3 is definitely less than 1. So M is less than 1. So that means the image is diminished. And also we studied yesterday that if M is positive, right? That means the image is, M is positive, that means the image is virtual and erect. Understood? How we linked everything, can you see? Can you see how we linked the whole chapter? Okay. Okay, next we have a little bit of a topic, power of a lens. We studied about focal length of lens, right? Now the ability, there is a lens. This is my lens, my eye lens, the lens in my eye. The ability of my lens or the ability of this lens to focus to converge the light rays, to focus the light rays coming and form it into an image. Now see, this is a lens, okay, and this is a lens. There will be a difference, right? This will have a greater focal length, so it will converge the light rays at a distance of, let's say, 10 centimeter, right? And this Moto lens, it has a focal length will be smaller, right? So its focal length is 5 centimeter. So all the rays coming parallel will be focused at 5 centimeter. So here the image distance is 10 centimeter. Here the image distance is 5 centimeter. So both of their power to converge the light rays is different. Right? So power to converge or in concave lens to diverge the light rays depending on its focal length. Is called power of a lens. Okay? Or the degree of convergence or divergence of light rays. How much, by what degree they were converged. This was converged at a higher degree. This was converged at a less degree. So the degree of convergence or divergence of light rays achieved by a lens is expressed in terms of its power. If power is 5 diopter, it can converge the light rays at, okay, power is equals to 1 by f. I'll come back to you. Power equals to 1 by f, where f is focal length. F is focal length. Understood? So power, this is power. That means the power of a lens is dependent on 1 by focal length. That means if focal length is more, power is less. If focal length is less, power is more. Its focal length is more, power is less. Because it can converge the light rays with less degree. The light rays are getting converged very far away. But here the focal length is small. The focal length is small, power is large. It can converge the light rays at a smaller difference with more power. Okay. So that is the phenomena of whole power. So the power of a lens is defined as the reciprocal of its focal length. That we studied. Unit of power is diopter. Now, very important thing, unit of power is diopter only when focal length is in meters. Okay, if focal length is in meters, then formula of power is 1 by focal length. If focal length is in centimeters, then power is 100 by focal length. So we just converted centimeter into meter and changed the formula. Okay. Now in both cases, the power of the unit of power is diopter. Understood clearly? And that is it. This is where we complete our chapter light. Light chapter is finally done, my friend. Now, if you have completed this chapter in your class, then I hope you understood it better. Because I know lots of time, because there are lots of kids in the class and you're like, ma'am, I don't understand anything. What are the rays? What are the diagrams? It went above my head. But in this chapter, I guarantee you that you will see this chapter very carefully. You will understand everything. Okay. So I hope you understand this lecture. And if you understood in the class, that is very well. If you didn't understand in class, it's good. If the chapter is still not complete in the class, then you are way ahead of your class, of your peers, and that is the best thing you can do. Okay, so that is it for this chapter, for this light chapter. It's a very numerical based chapter. I will do the videos on numericals as well. Do not worry at all. We'll solve all the numericals from the basics to the board level mastery. Okay, do not worry at all, and I'll see you in the next video. Bye.